Good day, ladies and gentlemen, and welcome to this worked example we're going to be doing, looking at the design of a tension member with bolts to SANS 10162. This is part of the Structural Design 424 Steel Design course at Stellenbosch University. To introduce the problem to you, what we have to do today is determine the capacity of a tension element. There is the example. It's a 150 by 150 by 18, grade 355 JR. There are 8 bolts, the M24, it's a 24 diameter in class 8.8 or grade 8.8. And then these are in 26 diameter holes, but we'll have a look at that later. It's bolted to a 25mm gusset plate, and the dimensions are given, and then we'll come back to these letters across the section. We're going to be looking at what is the tensile resistance of it. We're not going to be looking at the tensile resistance of the bolts or the bearing capacity or any of those. Just look at the pure tensile capacity of the system, and we're going to be doing this following the SANS 10162, which is in the Red Book, the South African Steel Construction Handbook Red Book guidelines we're going to be following. To make it a bit simpler in terms of understanding, I've also printed out here a sort of flattened version of this angle, where you can see I've just made the outstand, the unconnected leg, flat, and then we can also use this for understanding the different failure modes that we will be looking at. So here are the calculations we're going to start going through. So hopefully you have a copy of these, otherwise you can make it for yourself. There's the angle set up. And firstly, what we need to do is get the specifications of the angle. Even though we're told it's S355JR, the thickness is greater than 16 millimeters, and for very thick elements, the yield stress actually decreases. So here you'll see, I'm just going to zoom in for easier viewing of this, and here you'll see that because it's greater than 16, we're only going to yield strength of 345 MPa. That's obtained from table 2.1 of the Red Book, and with that goes our normal yield ultimate stress for 70 MPa. Along with that, we also need the gross area, which is 5,100 millimeters squared. That's table 213. And beyond that, also, we just need the specification in terms of the bolts. Now, we're told the M24, but we actually need to know what is the size of the hole we remove from our design. So first we want to say assume drilled holes, and this is because the thickness is greater than 12 millimeters. Thinner plates you can just punch, but punching you lose an extra 2 millimeters due to damage in the way it's formed and such. So T is greater than 12, therefore D equals 24 plus 2, so 26 millimeters that we need to design for in our section. Firstly, we're going to calculate our gross section resistance. So this is the resistance through any section here, somewhere along its length. Doesn't matter where it is, it's just the gross area times yield. So this is relatively straightforward. This all is outlined in section 3.1.1 of the Red Book if you want to go have a look at the calcs. So this is just the 0.9, which is our material factor, times by the yield, times 10 to the negative 3 to convert it to kilonewtons, and then this gives us a capacity 1,584 kilonewtons, which is a lot of load. It's 158 tons, so this angle is quite a heavy angle. It's 150 by 150 by 18 is not a common size. It would generally be used only for very heavy loads on the structure. Now we're going to start testing different failure modes. First, we're going to have a look at section ABC. So coming back to our cross-section, we're going to look at cross-section ABC all the way through. So this is our gross area minus the bolts. But then also when we check our sections, we have shear lag. And the fact that load takes a distance to spread out. So if we just sort of with a pencil mark out how sort of the load will spread out from the bolt, and it will take a distance until there is stress over the entire width. Because of that, we have shear lag. In fact, not the entire section is effective. So what we're going to be calculating now is the effective net area, which is something like that. So that would be the gross area is the whole thing. The net area would be the whole width minus the bolt. The effective net area is what I've just drawn there across that whole section up until where sort of some shear lag loss. So this bit here is lost effectively due to shear lag. Well, approximately speaking, we reduce it to account for that effect and the non-uniform stress distribution. So I'm going to now get that effective area across that section. So our ANE, our net effective area, is simply our gross area minus the number of bolts times the bolt width times T, and there was only one bolt width across that section. So this is quite a simple calc. Just make sure you always use the right thickness if you've got an element with like a I-beam with multiple thicknesses through it. So we end up with a effective area, or net area, of 4632 millimeters. However, now we need to reduce it for shear lag. And since there are 4 rows of bolts in a longitudinal row, it means that there's more space and more time for the load to spread out. Hence, we have a greater proportion of the load applied. I'm just going to show you the reference from the book. We're in section 313. For 4 or more bolts in a longitudinal row, the effective net area is 80% of the net area. So, just going to reference that. So, we're in section 313. And 4 rows of bolts, therefore, our effective net area equals 0.8 times our net area. Therefore, our effective net area equals 3706 millimeters squared. And this area is what I showed you a few minutes ago, that it is the cross-section with some area lost for shear lag. So it's about 20% approximately at the end we've lost due to shear lag effects and the non-uniform stress distribution. Now we can calculate our tensile resistance of the section. So our tensile resistance is simply 0.85 phi ANE times the ultimate stress. Remember, we're dealing once again with fracture and net areas with the ultimate stress, not the yield stress. So this is 0.85 times 0.9 times the area we've just worked out, times by the ultimate, and then convert it into kilonewtons, and we have 1332 kilonewtons. And already you can see the capacity has dropped a little bit versus the capacity calculated earlier. Then we can move on to looking at different failure zones and modes and such, and there are various ones that could occur. I'm going to first look at the net section along what we're going to call ABGD. So if we take this here, there's our cross-section. We've checked our gross area failure. We've checked our net area, where this is not fully effective, that last section. And then what we are going to do is come back to ABGD. So I'm just going to highlight that. So there's our section ABGD. This section we're going to have to be careful between B and G. It's on a diagonal, which actually means that it is both in shear and in tension. Now, the simplest way that the code accounts for that is, rather than treating it both in shear and tension, we treat it in pure tension and then add on a little bit of extra capacity and a bit of extra length due to the slope. And that sorts out the fact that we have more length than just the horizontal length. So we will do that now. Check out the capacity of the section. So there's our net section. So this is once again also now in experiencing shear lag. On net area, so this is the equation we want to fill out. Our net area is our total area minus the number of bolts passing through, plus a little bit of extra due to the influence of that slope. That's s squared over 4g times by t. I'm just putting this t separately. Be careful, it's very easy to forget to multiply it at the end. S squared over 4g is a length, a bit of extra length to account for the slope, and then to convert to a cross-sectional area, we have to multiply it again by the thickness there. So here we'll have the total area minus, now there's 2 bolts passing through. So there we go, we've got 2 bolts once again, there, and so we are now removing this area and removing that area from our calculations and only having then the remaining. And then shortly we'll also remove some extra at the end to account for shear lag, remaining with just that purple line. So minus, there's our total, minus 2 times 26, the bolts, times 18, plus s squared, which in this case is 60. That is the spacing longitudinally along the bolts, divided by 4g, 4 times 40, so that's the horizontal spacing between, times 18. So there's our 40 dimension, and then it's 7 at 60 spacing all the way down here. So 60 and 40, those are where that 60 and 40 dimensions come from. And if we work this out, we have a total area of 4,569 millimeters squared. And then from above, from C, which is our effective net area, equals 0.8 times the net area. So this is 3,655 millimeters squared. And now we can then calculate the tensile resistance. Based on the equation above, I'm just going to fill in all the numbers to that equation now. So we have once again, an additional capacity that we have to check. So this is once again a little bit lower than our previous ones, and we're trying to find the lowest capacity of all the different possible failure modes. All of this, if in doubt, you can check this from the Red Book, and we're all again once again in section 312. So I'm just going to make a note of that, section 312, if you want to go see where this s squared over 4g, and just always remember to multiply it by the t. Now we're going to continue on looking at block failure, looking along CBF, and there's a couple of areas I'm going to need to look at, because a block failure is whenever you have a section that pulls out. So part of it's in shear, parts of it in tension, and even part of it can be on a slope as well. And when we calculate the tensile capacity, the total tensile capacity has 2 points, a tension component and a shear component, either shear yield or shear fracture. And the tensile component doesn't matter. We've got to check both of these. The tensile capacity doesn't change. The shear yield or shear fracture base, we're looking for the lower of those two, and then use those for design. So we now need section CBF. There's our section once again. We can now check it all the way down. So we're going to have section CBF. That's all the way here, and then all the way down the side. When we calculate, if we have the gross area, the gross area includes the bolt holes. So this would be including the bolt holes, and the net area excludes those bolt holes. So you'll see there's 3.5 bolts, 1, 2, 3.5, that pass all the way through this failure line when we get the areas that we're calculating. So back to our calculations, I need a gross area in shear, a net area in shear, and a net area in tension, which we will work out. Now our gross area in shear is just this total length, 420 plus 60, so it's 480 mils. Times the thickness. So this is 420 plus 60 times 18. 8640 millimeters squared. Then we need the net area, where this is the area we've just calculated minus the number of bolts that pass through this area. So we just have to be careful. This is 3.5 bolts times by the breadth times by the thickness, and we have then a reduced area, so that's the net area in shear. And then once again we also need the net area in tension, so that is the small piece at the end, and that is then just the width, 40 by 2 minus half a bolt hole, and this is all multiplied by the thickness, and we have our area. So once again, what we've done here, looking at this pink outline, I've checked between B and C in tension, and I've excluded the bolt hole, and then this whole length, either taken the whole thing in shear or the net area in shear, excluding those bolt holes. And we will now start plugging those into the equations. Firstly, shear yielding, looking where the shear capacity is either the gross area at yield or the net area at ultimate, and this is when something's actually fractured. You take it right to the point of it fracturing or it yielding, and use different areas. So I'm just going to plug in the numbers now. And now we can get to our capacity of the section, which is 1610. Right at this point, we'll already see that this is not going to govern. This is higher than we've calculated above, and we haven't even added the tension in. But we're still going to keep going and complete this. We'll check now the net area in shear. And then this gives us a capacity once again, and this is what we call shear fracture, 1,777 kilonewtons. And then also we're going to work out then the tensile resistance of that section that was left over, just so we have all the details. And we will end up then with a capacity of 510 kilonewtons. So it's the minimum of these, shear yield and shear fracture, plus the tensile resistance that we need to include at this point. So I'm going to go into the next page to cover the last bit. So therefore, the total resistance is TR plus VR. It is two components. There's a tensile component and a shear component to what we have just calculated, and that will be 510 kilonewtons plus the minimum of the other two that we worked out, 1610 and 177. So obviously it'll be the 1610, and we have a total capacity of 2,110 kilonewtons, and we can make the note that shear yielding governs. So this, once again, is a distinct failure mechanism compared to the other ones. Then we're going to have a look at, just briefly, what about block shear in ABGE? So what happens if we checked ABGE? That would be similar to ABGD, except instead of having this shear area here, tensile area between G and D, we replace it with a shear area all the way down. Just by looking at that, you should see that the area between G and E, even minus the bolts, is significantly higher than DG. So this will be a lot higher, the capacity along GE. So by inspection, we don't need to check this, because we know, I mean, the fact that this area is probably more than 10 times larger than this. We can just make a note saying block failure along ABGE. And just so we can confirm, since EG is much greater than GD, failure ABGE will govern. Will not govern. And the failure plane we looked at will be lower. So by inspection, we can see that since there's such a large area and such a difference, that we're not even going to bother pursuing that one further. Then we also can have a look at block shear failure in DGBF. So coming back, DGBF. This is once again another feasible plane that could occur. We've got it all the way down here, up and across, and then all the way down the side. So very similar to the last one, except instead of the pink path between CBF, we just have the stepped path here. And if we pulled on our angle, what would happen is this section inside this green line would be left behind. So we're going to check that now. Once again, there's a shear capacity there and a tension capacity there. We have already calculated the shear capacity along that line between B and F, so we don't need to redo that. We will only need to check the tension capacity at that corner when it comes to our working out now. So here we go back to block shear along DGBF. Now, once again, BGD is in tension, B to F in shear, B to F in shear. Now, from previously, as I mentioned, we've already calculated the shear resistance from above. We already know that this is 1,610 kilonewtons, so we have those values. Now we just need to work out the tension capacity. So what is the tensile value there? Our net tensile area is going to be 2 times 40 minus, there's 1.5 bolt holes that passes through here, plus the sloping bit, which is S squared over 4G. And this entire section is multiplied by 18. So we have a total area of 1143 millimeters squared. So just to come back to that, we took our failure plane along that line, which is 2 times 40 minus 1.5 bolt holes, half and 1 going through, and then adding on for the sloped bit, S squared over 4G, then multiplying that entire width by the thickness of 18 mils, and we have our tensile capacity. And then our total tensile resistance is once again a tension component plus a shear component. Just remember, whenever you're dealing with shear, you'll often see this 0.6 or 0.66 in front. That's to convert the tensile capacity to a shear capacity. And let me just fill in all the details, plus what we've calculated previously, 1610, and we have a final capacity of 2093 kilonewtons. From all of this, we would have to check our lowest resistance and select that for the design, because there's various capacities we've calculated. We had our gross section of 1584, our net section of 1332, net with shear lag and net section ABGD, that's 1314, and then block shear and block shear, etc. So of all those different failure mechanisms, what we find is therefore net section A to B to G to D governs. And so our tensile resistance is the minimum value we've calculated so far, which is 1314 kilonewtons. So 131 tons is what this section can carry, and we've followed all the different mechanisms to have a look at it. So coming back to this, we've gone through all the different checks and found out that A, B, G, D is the weakest. Not surprising so, because we've lost the bolt hole along this path, although it would be close between these two, as you saw the calculations point out. And yeah, so that summarizes all the main details of how to go about shear calculations.